This is Larry Benko, W0QE, and this video is about designing an AM broadcast interference filter. The previous video I did described how to size components for a filter or a circuit, and in this video we will talk about the design of the circuit and not about sizing the components. In the United States and in many parts of the world, the AM radio band is just below the 160 meter band. And the 160 meter band generally is close enough to the AM radio band that it's not a trivial problem to remove interference. The interference that we see from the AM radio stations, other than if they happen to be a harmonic and we hear them in a band, is due to a process called intermodulation distortion, or IMD. Intermodulation distortion occurs anytime you have a circuit which is nonlinear and you have more than one frequency applied to that circuit. There will be mixing products involved, and the mixing products will produce signals, we can call them phantom signals, which occur at a frequency which really doesn't exist other than inside the radio. However, you hear them on the output of your radio. In the United States, we have AM radio stations that are allowed to run as much as 50 kilowatts of power. Some run that power day and night. They operate at frequencies from the low end of the radio of the AM radio band all the way up through 1600 kilohertz. And from 1610 kilohertz to 1700, I believe the maximum power is 10 kW. And that's day and night. Is something where some radio stations have to drop their power at night and some don't. So if you have IMD, you might have it worse in the daytime and not as badly at night. And again, the problem here is one of power and one of location. If you happen to be unfortunately located close to a radio station or line of sight to them, you're more likely to have a problem. Now, different receivers have different sensitivities to intermodulation distortion, but all radios exhibit the problem. No matter what the radio is, you can have a strong enough signal that the radio is driven into nonlinearities. In the case of most amateur radio transceivers that are the higher end transceivers, we have an alternate input, a receive-only input of a transceiver, and we can put a filter there. However, you may not be using a receive-only antenna, in which case then you need to build a filter that would go on the output of your transmitter and use some relays to switch in and out that filter when you're transmitting or not transmitting. Or you can build a filter that's tough enough to take the transceiver full power output. And that can actually be good because then the interference from the AM radio stations cannot cause your transmitter to have intermodulation distortion. That generally doesn't happen unless you really have terrible interference. You could also design a filter to fit on to be on the output of a high power amplifier, but that's generally not done. Some considerations to think about are you might take the approach, I just want to build a brute force filter that's so tough that it doesn't matter. I don't need any specs or anything else. I just build it. That's going to be tough because if you have a station really nearby, like 1680, 1690, 1700 kilohertz, you're going to need a lot of components, and it's a very tough filter to build. So I wouldn't spend my effort building a filter like that unless you had that problem. So you need to tailor the frequency response and the attenuation required. You can determine those values by putting an attenuator in front of your radio, a resistive attenuator. You can also use the input attenuator in the radio if it's truly resistors inside of there that are switched in by a relay. And when you put a 10 dB attenuation in front of a circuit which produces intermodulation distortion, products that are intermodulation distortion products will drop by more than 10 dB, typically 20 to 30 dB. And that's one way to identify them. You can also think about the filter as whether or not you want it to be capacitor input filter or inductive input filter. If the inductors are on the ends, you will probably end up needing one more inductor than you have capacitors if you want to make the filter symmetrical. But you'll be able to bleed static away from an antenna that way. That's entirely your choice. In some cases, you might want to put this filter on the output of a transceiver, transmit through it, and you want to leave it in the circuit for all the HF bands. So you need low SWR over the entire passband. And as a suggestion, if you're building one that goes to a higher power, is going to go in a higher power environment, prototyping it as a receive-only version, using smaller components, might be a wise place to start if you're not real comfortable in building stuff. I'm going to do a little demonstration on IMD here to start, and then we'll get to building the filters. And here's an example of intermodulation distortion. I put together two signal generators. The first signal generator is operated at 2.19 megahertz. And we can see it's right here. And it is an AM modulated signal modulated with a 1 kilohertz waveform. And then I have another signal generator. And it's here. And it's an AM modulated signal also, but it's modulated at 400 hertz. And each one together produces what you would normally expect for a spectrum. And together, they produce all kinds of intermodulation distortion. The two generators are hooked up exactly in parallel, and the output of one generator affects the other one. And then what we see is the corresponding intermodulation distortion that we get when that happens. And it's worse than just right here, because if we look up at the harmonics and look at this spectrum again, let's just look at the whole spectrum. Spectrum's pretty clean. And now we get up to double the frequency where we were before, and we see again a set of intermodulation distortion products. And there it is again. And again. And you can keep seeing more, and they go on and on for quite a while. Each set is lower than the previous set in amplitude. But my original group right here were S9 plus 50, and this little SDR that I've got this hooked to shows it shows this intermodulation distortion down, like in this range down here, 40 or 50 dB below this, when I combine the two in a nice manner with power combiners and attenuators on the output of both generators. These two generators are both hooked directly in parallel, and then there's an attenuator on the output to produce the IMD. But this is what you get with IMD, and it occurs anytime you have strong signals nearby that cause some nonlinearities in a circuit, particularly your receiver, and then other products mix with those, and the next thing you know is you hear stuff where it really doesn't belong. For the first example, let's use the requirements of the filter is a receive-only filter, which means we will allow a little bit of loss in the passband, and we'll allow more SWR than we would have allowed if it was a transmit-through filter. And for frequencies below 1.3 megahertz, we're going to assume that the attenuation is at least 20 dB. And for frequencies between 1.3 and 1.5 megahertz, the attenuation is at least 10 dB. So let's add some frequencies. Each frequency that appears in here will have a dot on the square chart. And to make things easier to adjust and to play with, we have 1.3 megahertz as a frequency that's important, 1.5, clearly 1.8, which is the bottom of the 160 meter band, 2 megahertz, which is the top, and we'll finish with 1.9 megahertz. The reason for finishing with 1.9 is the last frequency in this list becomes the frequency which is used if we add a component that has a frequency in the component. And I don't know if we'll add something like that or not, but anyways, I put them in that order. We see the frequencies here, 1.3, 1.5, 1.8, 1.9, and 2 megahertz. And if you're not familiar with the requirements that we have imposed on this design, let's start off with a relatively low complexity filter. It's a Butterworth filter, which I've done. I set it up to be, I just did this in LC. I set up the 1.8 megahertz loss to be 1 dB, which it came out to be 1.03. We have a passband SWR of 2.6 to 1 at the low end of the band and 2 to 1 at the high end of the band. And we look at our attenuation at 1.5 megahertz at 2.48 dB and 1.3 megahertz at 4.44 dB. And we realize that this is woefully inadequate for what we're looking for. So, and before I get too far carried away here, let's look at some filter types. This is just a page on Wikipedia. This is the characteristics of like a Butterworth filter, which I built, which is monotonic in both the pass band and the stop band, no ripple. Chebyshev type 1, which is the normal Chebyshev filter, which is ripple in the pass band and monotonically decreasing in the stop band. Chebyshev type 2 is monotonic in the pass band, has ripple in the stop band, and elliptic or Cowher filters have ripple in both the pass band and the stop band. So let's go to another filter now, and I'll put an extra load generator block here, and let's load another filter. I did a Chebyshev filter, and we need the SWR here at A, and the orange and the light blue one are for the original filter, the Butterworth, and then the purple or pink and the blue are for the new filter. So the new filter, the Chebyshev filter, is better. It has better roll-off. So it at 1.5 megahertz is down to 5.79 dB, and at 1.3 megahertz, 10.6. So we're getting closer, but we have a ways to go yet. It has a better SWR in the pass band, marginally at 1.8 megahertz, but it's better at 1.9 and 2 megahertz. And let's see what else we can do. Keeping along the lines, and both these filters were, both these filters were the same topology. They were just a 2 capacitor, 1 inductor, high pass filter. So let's delete this one because we've decided the Butterworth is inadequate. And we're going to replicate the one I was just working on. So now we have two curves on top of each other. You can't see the curve, but it's there. And the SWR curve is matches too. So let's take the second one here, and let's see what we can do with a 3-component filter to see if we can improve the loss. Now we can continue to guess at filters, but SimSmith has the really nice characteristic that we can, in real time, just move stuff around. Now both of these filters, and this is true of all Chebyshev filters and all Butterworth filters, they're symmetrical. And it's not until you get to different, more exotic filters that the components become different. So the two end components will have the same value. So they're both set to be C1, and L1 is set to be L1. So there's only two components that change in this filter. A C1 component, which adjusts both capacitors, and an L1. So let's start making this filter a little bit better. You can see as I decrease the capacitance, but yet still re-resonate it, it becomes a better filter for what we're looking for. Let's do it some more. Now what we're trading off here is steeper roll-off, still okay pass band SWR, but higher ripple in the pass band. So we have ripple here in the pass band that's down 3 dB. There's at least 3 dB of ripple in the pass band, and we're specifically trying to put our intended frequency range right at this little peak here. So let's drop it even some more, because we're still not down to 10 and 20 dB. This is getting better. Not quite. Okay, we've exceeded what we needed by a little bit here. Let me go up a little bit here. Okay, so let's look at this filter, and I'll turn the first filter off for the moment. And what we have is we have passband loss that ranges from a half a dB in the middle of the band to 2 dB, a little bit more than 2 dB at the ends of the band. SWR in the band of 3 to 1, 3.4 to 1 or better. But we have our, at 1.5 megahertz, we have a loss of 14 dB, which exceeds our 10 dB number. And at 1.3 megahertz, we have loss that is 0.7 dB more than what we asked for. So this would meet the spec. It may not be a filter you'd like, but it's perfectly adequate in a receive-only application where this amount of loss in the receiver wouldn't hurt anything, and this SWR wouldn't bother a receiver at all. In a transmit application, this would probably be unacceptable. But let's see what we can do if we're willing to add another component or two. And let's add 2 more components. So I'll get rid of this original filter again. I'll move this one over here, and I'll bring a new filter in. And this filter, just like the previous filter, is a symmetrical filter. We have a capacitor on each end, which we're going to call C1, same value, a different one in the middle, and 2 inductors, both of the same value. We can think of this as 2 filters like we had before in series, where the this capacitor represents the end capacitor of a 3-component filter and a beginning capacitor of the other filter. So this capacitor should have be a lower value because it's 2 capacitors in series. And I've played with this for a few minutes, but it's not very hard to play with it. And came up with, it's pretty well adjusted right here. So I have a passband SWR. Here I can set the passband SWR now to be basically about 1.6 to 1 over across the band. My passband loss is 0.56 dB to it's a little over half a dB. We have 1.5 megahertz loss of 9.9 dB. It's pretty close to meeting the spec, and this is pretty close too. Let's just say that that's good enough for the moment. But what I've gained by adding 2 more components is a little. Let's bring the other filter back up. The 2 extra components gave me better passband loss, steeper roll-off angle, although I didn't get it all here yet, but it's a steeper angle going down, and better SWR in the passband. So if that's the case, we could add 2 more components. I mean, we can stop anywhere we want to stop, and there's no right solution to these types of problems. And let's bring up another one. And here's a 7-pole filter, I think. Let me look at that one for a second here. Yep. Just like before, once again, I've added another inductor and another capacitor in there. The 2 end capacitors are the same, the 2 center capacitors are the same, the 2 end inductors are the same, and the center inductors different than all the rest. And consequently, we have 4 components to adjust. And that gives us a filter which is the pink filter. We can see its passband is even steeper yet. And it doesn't quite meet the spec yet. Let's see if we can do something along the lines to make it be a little bit better. Let's drop that capacitor by a couple notches. I'm adjusting in magnitude values of 1% or a little bit less. I keep moving that back up when I get the SWR down. If I care to get the SWR down, if I don't care to get the SWR down, I can let this be. I meet the spec just fine here, and the SWR is a little bit higher. This is perfectly fine for a receive filter. If I wanted to turn this in to a transmit filter, though, I would need to be a little bit, probably a little more careful here. I mean, this is the power of SimSmith. This is pretty good here. I mean, this was me just clicking on a component and moving the mouse wheel and watching the graphs. Now, I may have more experience doing this than you do, but it's something anybody can do. The only thing that I can do then is do it a little bit quicker than you can do it, and I know which way to set the components. But again, that's it's not something that only a certain person can do. Anybody can do it. The only thing is, as you get better at it, you get faster. So this filter with 3 inductors and 4 capacitors will have passband loss of less than half a dB, about 0.36 dB and 0.31 dB, in-band SWR of 1.05, 1.1, 1.1 basically. And this would be good for a transmit filter. It's got attenuation at 1.5 megahertz of 13.1 dB, which exceeds the spec. And it's got attenuation at 1.3 megahertz of 28 dB, which exceeds the spec by quite a bit. It has in-band SWR of 2.5 to 1, so you wouldn't want to use this filter over across the whole HF range. Now, if we added another pole to this filter, we could continue to reduce this lobe and still maintain a fairly sharp cutoff, and I'll show a filter of that in a little bit. But the idea here is that play with the filters. I would use a program like LC, which is free. It comes with a handbook, and an LC filter of size of order 7, and this is an order 7 filter, is the maximum you can do without paying money for the filter or for the program. But you can get an idea of the component values. You can put those in a SimSmith circuit, and then you can start playing with it, and you can adjust it then to your requirements. And this filter is a pretty nice filter. What would happen if we changed the component values by 1%? This is 1% change. Up and down, that's not too bad. And that's changing both of them at the same time. 1% up, 1% down, same thing, not too bad. 1% up, 1% down, not too bad. I mean, the component sensitivity is not too great. And that's nice. So this would be a pretty reasonable filter to do. The 2 pictures here represent, this is a receive-only filter. It's not quite what the 5-pole, it is a 5-pole filter. It's not quite what the one we had just a few minutes ago was. It doesn't have quite the roll-off, so it's not quite as aggressive. But it's built in little Pomona boxes like 1 by 2 inches with a couple of T50-2 powdered iron cores and some silver mica capacitors paralleled up. Actually, these are paralleled up. These were standard values, and I adjusted the filter to meet a standard value. And that's another thing you can do if you have a few dB to spare. This filter right here represents the next filter we're going to do. And it's something I built a few years ago for a guy who had a very good antenna site that he had line of sight view to a lot of different radio stations. He had huge intermod problems. And this filter you can transmit through at 100 watt level. It's a 9-pole filter. The capacitors are parallel to give me the right values. And this big wide strip in here was to maintain better SWR. But this filter was to stay in all the way from 160 through 10 meters and have low SWR at the higher bands, so you didn't need to switch it out of the circuit. And let's look at that circuit right now. And there it is. It is designed to be a transmit 100 watt plus level of 100% duty cycle over the full HF range. It's intended to have an attenuation below 1.3 megahertz of 30 dB, and it meets below 30 dB, and from 1.3 to 1.5 megahertz of 15 dB. And we can see at 1.5 megahertz it's 15.8 dB, and at 1.3 megahertz it's 33 dB. So it met the spec. It's got good passband SWR. The worst passband SWR is 1.3 to less than 1.3 to 1. And over the full HF range, it had low SWR and it had great low insertion loss. Now this circuit was built and and measured. Looking at the graphs, we can see that the measured results match the predicted results quite closely. The loss at 1.8 megahertz was supposed to be 0.56 dB. Excuse me, the measured loss was 0.56 dB. 0.54 dB is the predicted loss. At 2 megahertz, the loss is 0.4 dB, and at 2 megahertz, the loss was predicted to be 0.34 dB, which is extremely close. And the SWR, we look here across the whole frequency range, and it's less than 1.2 to 1, and here the entire SWR is less than 1.2 to 1, although it shows it rising here at the very end a little bit to be just about 1.2 to 1. So anyways, it's got a good SWR. It matched what we tried to design, and I would attribute that primarily to the fact that this is large. These inductors had pretty high Q. They were measured and tweaked turn spacing wise by putting a network analyzer cable in here. With this piece out of the circuit, I went in here and measured the inductance to ground on each one of these independently with a cable I'd calibrated to the end with the lid on, and then I put this piece in afterward. And it was spot on just from the measurement. So that was a success. And it completely killed the IMD at this station, and it worked very, very nicely. This filter is chronicled in a little more detail. Losing track of everything here. I got a little more detail on it on my website. Here, where it was designed in LT Spice because I was not familiar with SimSmith at the time I did it. But reproducing the results in SimSmith gave me results that were very, very close. But anyways, this is the filter. And for the last example, I don't really have a spec for this one, but let's just assume this is just a non-ruse block version of what we did in the very first example, which was the 5-pole filter in the first example, with the same component values pretty much. I'm not sure they're all exactly the same, but it's hard to say. We're going to change them anyways. I think they're about the same. I'm going to assume here that instead of worrying about 1.3 and 1.5 megahertz, we're going to worry about 1.7. You are one of those unfortunate people who happen to have a 1.7 megahertz radio station near you, and you still would like to operate 160 meters. This is a tall order for a filter to give you much attenuation. Let's see if we can get 10 or 15 dB of attenuation and still make the passband look decent. I know from experience that this is not going to happen with a 5-pole filter. It might not happen with a 12, 13, 14-pole filter unless we have some resonant circuits in there. So I'm going to pick one of these series capacitors. It's not really important which one we pick. I'm going to pick one and I'm going to put a resonant circuit in there. And we're going to set the frequency of this resonant circuit to be 1.7 megahertz. And we're going to lock it. So as I tune the components, it stays at 1.7 megahertz. Now here I have a very nice notch at 1.7, but here at 1.8, 1.9, and 2 megahertz, the filter has got way too much passband loss. So the first thing I'm going to need to do is increase the capacitance here, which is heading in the right direction. We need to increase the inductance, I think. This is unscripted, so it's going to take me a while to get this right, probably. Increase the inductance in the middle here, too. That's maybe too much there now, I don't know. The end values are pretty good, I think. Let me make them about equal, just for grip. Trying to make them equal here, just because I was making everything equal before. All right, I think we need to increase the size of these inductors. Okay, we're getting closer. Yeah, this is getting better. Now I'm allowing all these to be independent, but I'm adjusting them, trying to keep them roughly the same. Well, this isn't too bad. Passband loss of less than 1/10 of a dB, 0.14, 0.33 at 1.8 megahertz. A notch at 1.7 megahertz of 22 dB. Let's zoom in on that notch and see how wide. At 20 dB, it's pretty narrow. It's a pretty narrow notch. The component sensitivity here is going to be pretty bad. But this would work. If you needed a little bit less than, say, 20 dB, like maybe 15 dB, a circuit like this could work. And one of the things we can do here is we can change all these components by 1% and see what the effect is. And I'll unlock that when I do this. And if we up and raise this one up 1%, down 1%, it has a little effect, not too bad. Up 1%, that's up 2%, down 2%, up 1%, down 1%, up 1%, down 1%, not too bad. Up 1%, terrible. Down 1%. This resonant circuit is extremely critical here. So you would need to match this. Although having the frequency matched is important, but having the actual component, if I move them in lockstep, 1%, it really makes very little difference. So you would need to make sure that this was resonant exactly where you wanted it. But this is, if you live in a place where you need 20 dB of attenuation 100 kilohertz away, and beggars can't be choosers here. You can't be quite as picky. You could actually transmit through this filter too, just fine. And if you actually had a station that was that close to you, you might want to transmit through it. I don't know what the signal would be in your to your transmitter, but if you have real strong broadcast, it's entirely possible that your transmitter will generate IMD just like my initial IMD generators did, if you have a strong enough signal. There's a myriad of things we can do here in SimSmith that'll let us achieve the kind of stuff we're looking for. It helps if you have an idea what kind of a circuit you want, then play with it in SimSmith real time. I mean, that didn't take too long to come up with those values. I kind of knew which way to go, but the whole deal, you have to change all these components to get rid of the effect of this. This does not look like a capacitor. Before, when we had a capacitor here, it was a capacitor only. And by putting this inductor in here and making this resonant, moving 100 kilohertz away, this is not a capacitor yet. It's capacitive, but it's not enough of a capacitor that these components can be the same values as they were before. If we had looked for a notch down here, we'd have been able to just put a notch in here and hardly adjust these at all. But being able to play like this in SimSmith is an incredibly powerful tool. And there's no way in the world I could have put the parameters into a program like LC and gotten a filter like this out of LC. Now, there are some very high-end filter design programs that you can specify a range for, passband range everywhere, but those are, probably out of the price range of what you're looking for. And this works this works very, very nicely. These kind of trial and error, do-it-yourself type filters and designs are things that I gravitate to a lot because it's pretty easy once you get enough experience to just crank them out almost faster than you can bring up another program and put the values in. So I hope everyone's enjoyed this video. Appreciate it if you haven't subscribed, if you would please. If you like the video, please tell me you like it. If you don't like it, let me know. And if you have some suggestions for other things, I would certainly appreciate the suggestions. Thank you very much.